Say yes.
Okay. Thanksgiving is just one of those days. Let's see. We just have 3 lectures left. I think that's right. There are 3 lectures. 3 lectures left. And yeah, so I'm going to spend this week talking about biochemistry. I've got 2 lectures for you on biochem, and then the last lecture may be more biochem. I may change the topic. We'll see how we feel. We could do a whole class on kinetics. If there are real whole classes on kinetics, we can certainly talk about it. So I have to kind of pick and choose my topics. But I think what we'll talk about today is in particular the importance of catalysis and how catalysis plays a role in biochemistry. And I'm not going to do a lot of biochemistry, but so we're going to talk about the kinetics of these things and talk about the way that biological or biochemical catalysis works from a physical point of view. Instead of really focusing on structural biology and what a protein is and what an enzyme is, maybe we could talk about that a little bit more if you're interested. Let's just try to understand mechanically why enzymes are so powerful. Bioorganic catalysis is such an important part of the body or any living being. Of course, when I talk about biochemical catalysis, what I'm really talking about are in particular a certain class of proteins, which we call enzymes. Right. I gave this on Tuesday. And it was a really sloppy lecture, so hopefully it'll be a little better today. I'm not a biochemist. I'll be honest with you, I got a C+ in biochemistry. It was my last chemistry class in my undergrad. I had senioritis like a motherfucker. And I kind of checked out. But I've learned an appreciation for protein science as I've gotten older. So I'll try to share this with you. But we'll look at this from a physical chemist point of view. But I think it's important to think about what enzymes do for us. And one thing that you learn when you talk about protein chemistry and enzymes in particular is 2 things. One, it's an evolutionary point of view. There are lots of different enzymes, and in some sense, every enzyme basically does different things. They target different molecules, different processes in a living organism. To facilitate some chemical reaction. And some of the enzymes in our body really only do one thing. They target one specific, say, sequence of amino acids when they're breaking something down. Look at different types of proteins. Some proteins put things together, some enzymes put things together, some enzymes take things apart. So they catalyze all sorts of different processes. One of the things that's really interesting is that despite the fact there's this what we call divergent evolution in proteins, which is that proteins evolve in some sense separately to do very, very specific tasks. And as we'll see, they do them very, very well. They share motifs. So proteins that do similar things have similar structural properties. They have, I'll talk about it. The way that they do things is convergent. They all share a common motif in some sense. If they all kind of imagine you have a set sequence of proteins, different proteins or enzymes that are mostly meant to break down other proteins. They cut the amino acid and protein across some amide bond. So they cut it in half, they cleave it, and different enzymes cleave at different places. But what you end up finding is that the mechanisms or the structure of that protein where that job gets done, that enzyme gets done, all of those different types of enzymes, they have similarities in how that kind of central mechanism looks like structurally. So they share a lot of different motifs, and that's because they share kind of a common set of chemical principles, and they ultimately have to do the same thing, but different targets, so they all look different, but when you get down to the nitty-gritty, they're all quite similar. So it's really interesting how biochemistry, I think that's one of the more fascinating things, is there's so much diversity in biochemistry, but in some sense, the key motifs are shared amongst classes of proteins. So let's look at an example of an enzyme. Really common example. And again, I don't want to focus on the different types of enzymes there are. I just want to look at a really common example of one. And one I want to look at is what's called lysozyme. Right? And lysozyme is everywhere. You find it everywhere in the body. It's secreted and it's a part of the immune system. It's an immune system enzyme. Right? And you find it in all sorts of things. It's in tears, saliva, breast milk, mucus, etc. Right? Your body just has it anywhere that it's going to suck up dirt and bacteria. Your body expresses this lysozyme enzyme, and it's in your secretions, right? And the idea is that it breaks down foreign material. It's a recycler of biochemical material. So what lysozyme does, we can just kind of talk about it chemically, what the mechanism is. Is that it breaks glycan, so it cleaves sugars. So polysaccharides in particular, things that are containing multiple glucose molecules into smaller chunks. That are later processed and metabolized. So you've got this, like, you just ate a Twix bar, and you've got, you have all these really processed sugars that are really long chain polysaccharides excreted. So you take this stuff and there's another type of lysozymes or lysozyme class of molecules in your stomach acid called now I can't think of the name of them now. I'm sorry. I have it in here. I'm sorry. Tell them not a biochemist. The trypsins, which break down amino acids. And we'll look at the trypsins hopefully by the end of class, if not on Wednesday. And the idea is very simple. You have a polysaccharide chain. So I'm going to draw a very simple sugar. So this is a glucose molecule. Acetylated glucose molecule, a nitrosylated. I'm missing an OH here. The polysaccharide continues there, and each of the saccharides are linked through this ether linkage, or called a lactose linkage, through this oxygen here. And it continues on. All right, so we've got some complex polysaccharide that you've taken from your Twix bar. Right? And you need to break this down. Right? You can think it's just this long polymer chain. You guys know what sugar looks like, fairly soluble. But the idea is that you want to basically break this down into its smaller components, because eventually you're going to take that glucose and you're going to put adenosine triphosphate on it, and it's going to go into the Krebs cycle, and it's going to do metabolism and do energy. There's a big long cycle. You spend an entire semester in biochemistry studying that cycle. Right? But the first step is that we got to break this very long chain into smaller parts that your body can start to munch. And what lysozyme does is just this. It's a catalyst that cleaves the bond right here. It cleaves right there, cuts it in half. And when you put this in the presence of lysozyme and H2O, of course, since it's a body, you cleave this in half. I'm just going to kind of roughly draw this. You get an OH here. NH, CO, CH3. Just clean. And on the other side, I have the same thing, right? I cleaved it into two, another one. So I'll just write another one. Because the idea is that each saccharide oligomer is the same. And you cut it in half and you make this into an OH. All right, so what this does is it basically hydrolyzes this bond, right? It does a hydrolysis. Of the ester linkage. This is an ester, kind of an ester-like linkage. All right, and of course the question is why do you even need an enzyme to do this? Well, let's look a little bit at what the mechanism, if you were to do this in organic chemistry, how would the mechanism for this look like for an organic chemist? I'm not going to draw everything. I'm just going to draw the important parts, which is this O and this O linkage like this, right? There's a bunch of other stuff on here. Just kind of, there's some other things sticking out. So blah, blah, blah. Right. So of course the question is how is this mechanism facilitated? Well, the idea is that you want to cleave here, right? So we need to make this O into an OH, right? So we need to have that O have another, basically we need to cut this bond here, and we need to put an OH here. Right, so ideally the intermediate that we really want to use, we really want to generate is OH plus. Because this can kick this out, right? Kick this out, and then we get an OH. Plus here. And an OH on the other side, right? So ideally, we want to do this under acidic conditions, right? So this is catalyzed by acid. And the idea, of course, is that OH can come in here. Sorry, that's not how that works. You can attack that, right? And to regenerate, sorry, that's not the right place. I apologize. Actually, sorry, it goes in. So this is nucleophilic. Attack here. Sorry, I have this going the wrong way. And this is a negative charge. As you can see, I can't do my math particularly well. This is a minus sign here on the OH. And now we can attack from a nucleophile, and we now generate right, we get an OH group on both saccharides. Right? So this is catalyzed by acid, but right, so the way that we would do this in an organic lab is we would take this polysaccharide and we'd stick it in an acidic solution, and it would just fall apart naturally. Of course, this is at equilibrium, so I can't really write this. We'd have to consider some about the thermodynamics. Of course, this is at equilibrium. Right, but here's the problem, right? This requires acidic conditions. Right? But we're in the body. We don't have that luxury. In most parts of the body. Right? Of course, in the stomach we do. Because typically the pKa for these materials is usually around 6.9, right? It's pretty close to neutral. So it's not particularly acidic, right? So this is not an effective reaction biochemically. So this is going to be slow. Because it's catalyzed by acid, this is slow in the body. Right? So in order to facilitate just breaking down our big sugars, we have to have acid, right? Or we have to find some other catalytic source, something other than a proton. Of course, eventually we're going to need a proton, but maybe there's a better source of protons biochemically than water, right? The idea here is that the water, right, you have hydronium ions, right? It's just Bronsted-Lowry acid-base catalysis. We have some acidic water. It's acting as a proton acceptor and a proton donor. But maybe there's some other object biochemically that has a more labile H, a more labile proton that we can pluck off. It's more acidic than water is, right? Something locally more acidic. And the thing is that there are amino acids that are protonated at 6.8 that can provide that hydrogen. And so the idea is that in biochemistry instead, right, we rely on protonated amino acids to provide our source of protons, right, to catalyze this reaction for catalysis. Of course, the problem is that we don't just have amino acids floating around, and it's much more complicated, right? The amino acid needs to be in the right place at the right time, and it needs to have the supporting structure to ensure that this molecule comes in and binds effectively with that proton donor, that amino acid. This is where the enzyme plays the role, right? The enzyme, in some sense, is a framework, a structure, if you will, that provides, in this case, that proton, right? It also provides a way to suck that proton off, and also, that was a really bad way to say that, I'm sorry, to extract that proton afterwards to recover it, and also to provide a nucleophile here, right? We have two steps. We have a protonation and a nucleophilic attack. Right, so this is actually a two-step reaction. In order to cut this in half and create these two monosaccharides identically, we need to have two attacks. We need to protonate to cleave, and then we need the nucleophilic attack with a base. This is a base, and I think this is base. And this is provided by an acid. Right? So we need a nucleophile and an acid in our mechanism, right, in order to facilitate this reaction. So our catalyst needs to provide the source of, in this case, from Lewis acid, we need a electron acceptor and electron donor. Right, so enzymes are the scaffold, if you will, that provide the necessary components for the reaction, and provide them long enough, and they last long enough to do meaningful work. Because the idea is that if this sugar is moving around, it's diffusing around randomly in your body, some, like, you know, in your bloodstream, and you've got some enzymes that want to pick it up and process it, right? They might come and meet at some point, but that sugar's got to stay there long enough that the protein can do it, the enzyme can do its job. If the sugar comes in and just bounces off, they're not really interested in each other, then the enzyme's not going to be very effective, right? At the same time, if the enzyme really, really likes the sugar and doesn't want to let it go, that's also a really bad enzyme, because you want the enzyme to release the saccharides out, right? It wants to just do a job and then remove it and then go to the next polysaccharide and do the job again. Right, so let's just look at, just as a brief picture, let's look at what lysozyme looks like. If you've done biochemistry, basic biochemistry, you've probably thought about hen egg lysozyme. This is like one of the classic proteins that we learn. This is the lysozyme out of hen eggs that does this process. And you can see it's a fairly complex molecule. Each of these are actually chains of amino acids and strands of unstructured amino acids. But there's a number of amino acids in here. There should be a list of them somewhere on this page. Right, so there's 129 amino acids that are in a long sequence. And the idea is that there's somewhere in this structure is designed to effectively bind to its target as effectively as possible. It has been evolutionarily designed through whatever process you want to imagine in your head of taking 129 amino acids and putting them in some arrangement that creates this structure naturally in water. That process of taking a bunch of amino acids and making this complex structure, which is called protein folding, is an entire class on its own. Right? But the idea is that this is form some arrangement so that when you bring in this polysaccharide, that polysaccharide comes in and finds a really nice pocket to sit, and the nearby amino acids on the protein have the capabilities. There's a proton donor, there's an electron acceptor, right? It has the nucleophile, it has all the little components nearby so that these things can be shuttled in and out and cleave the molecule. And typically what happens is that as these molecules, these proteins are not rigid. So they have some structure, and then the target comes in, the polysaccharide comes in, and the thing establishes a new conformation to grab onto it sometimes, called induced fit, reacts, and then reisomerizes to kick the molecule out, right? So there's like a free state and a bound state, and they have different structures. And some very complex proteins have very, very interesting dynamics of folding and things like that as you go through it. Some things are very rigid. It really just depends on the system. Right. So there's not a lot we can get from this from a physical point of view, but the idea is that we have divergently through evolution just a long class of these proteins that do one task and they do it extremely well. And they're catalysts, right? Which means that they don't participate stoichiometrically in the reaction. Right? They're little machines that do a job for us. Bring in a molecule, kick that molecule out, they're ready to go for the next one. All right. And the most important thing, I think the take-home point really about enzymes is that enzymes are really good at this. In fact, enzymes are the best. There is no better catalyst than an enzyme. That may not be true, but generally I think that's probably the case. I want to show you a really interesting plot, or rather a table of some numbers. And this is a table of a series of different enzymes, really common ones. We won't go through the list, but they all kind of do the same stuff. We'll see they're all a specific type of enzyme or different, well, they all kind of have similarities. And this is a plot, this is a table of how fast the reaction is with the enzyme present versus not. So this just as a reminder, this is the rate catalyzed divided by the rate uncatalyzed. And this is probably not always the case, but my understanding typically is when you see ACE, this means it tears something apart. This means it's a cleaver. It cleaves something in two. Right. So a lot of these are most of these I think are, almost all of them are ACEs. Right. So they do some sort of cleaving reaction where they break a bond. And you can see the catalysis ranges anywhere from a factor of 100,000 fast and uncatalyzed to a number that I don't even know the name of. 10 to the 17, what's that? I don't know. Billion is 10 to the 12, quadrillion, quintillion. 7.2 times 10 to the 7.2 quintillion times faster. No, that's wrong. It's actually past that. It's 720 quintillion times faster. Even Elon thinks that's a lot of numbers. So So that they're really, really good, right? This is basically, I mean, I can't even, right? This is basically something, you have to think about what the actual rate of catalysis is, but as we'll see, the fastest that proteins can generally do things is about 10 to the 9. So the fastest rate you can get is about 10 to the 9. So if, let's say, for instance, for sweet potato, the amylase in sweet potatoes has a 10 to the 9 catalytic rate, which means that it generates 10 to the 9 molecules per second per liter. Right? This means that without that catalysis, it's 10 to 17 slower. That's 10 to the minus 8. Right? So that would mean that it would take per liter. Sorry, let's start over again. So the fastest these things can typically go is 10 to the 9 moles per liter. So is that right? Or is it moles? Yeah, it's moles. So if you have a liter and you have a molarity of your, this is kind of a ridiculous thing, but everything's at 1 molar. This means that amylase, the fastest it can generate is 10 to the 9 moles per second per liter, which of course is a ridiculous number. But bear with me. You can kind of get a sense of how that's pretty fast. That's 1 billion molecules a second, roughly. Right. And so it says without that, it's 10 to 17 slower. So that means roughly it takes 10 million seconds without it for 1 molecule to form. So you go from 10 billion molecules a second to 1 molecule every 100 million seconds or something like that. It's a huge difference. Right. So very, very effective at what it does. All right. There are other numbers that are interesting as well to correlate, but every metric I give you for an enzyme makes man-made catalysis look bad. It makes them cry. In fact, there's an entire field of catalysis where they do what's called biomimetic catalysis, where they go look at proteins that do a certain task and come up with something that they can make in lab that does it in a similar way. Sometimes you develop proteins and antibodies express certain types of antibody or certain types of enzymes and antibodies that do a specific function for you. There are medicines that are designed like that, that just do it better than anything that you could ever design without biochemistry, just organic ligands and metals and things like that. It does it amazingly well. A really good example of a medicine where the medicine itself is injecting yourself with enzyme to increase the amount of stuff you have, or rather, but this is a good example. I don't have a picture of it, unfortunately, but this is a new medicine that just came out in the last 10 years. Oh, you can't see it. I'm sorry. Called Ajovy. It's a medicine. It's an injection used for migraines. It's one of the few FDA approved preventatives for migraines. Most migraine medicines are abortives and at the moment, like on the fly treatment. This is a medicine that's used to prevent. And it's literally the way that it's designed is they take a certain type of antibody and they design the antibody around attacking a specific or inhibiting a specific function, some sort of protein or some sort of enzyme. And what the antibody will do will generate a new peptide that does that exact function. Give the antibody some task to kick in, to do immune response to it. It generates a drug, an object that does that job for you through antibody response. And people will extract that object, that biochemical object that these antibodies make, which sometimes are peptides in them, and they're enzymes in themselves, or there's some special peptide, some special sequence of amino acids that fit perfectly into an enzyme to turn it off or turn it on. And these medicines work extremely well. They're also horribly expensive because in order to make this medicine, you can't just put a bunch of stuff in a test tube, right? Like a reactor into it. Like for instance, a good example of a molecule where you could do this would be Ozempic. Ozempic is also a peptidic molecule. It has amino acids. It's a big long series of amino acids. It's made kind of in a solid state way. It's made kind of like Lego bricks. They make the sequence in like an iterative way. They make it smaller. They make it bigger, longer. Ajovy, you have to have, it's made, the factory is an antibody. It's a living object that generates it for you. So you have to culture these antibodies to get them to make the drug, and then you have to extract the drug. These cost a lot of money. My wife is on this one, and I think if it wasn't for insurance, it'd be something like $1,500 a month, one shot. Very expensive. But that's because, again, it's expensive to make. You have to extract it from a living object. Okay. So let's talk a little bit about the mechanisms of this. So we'll probably spend the next lecture or so talking about how enzymes work and the different types of enzymes and how we can tell them apart. All right, so let's talk about enzyme kinetics. And we're going to tackle this problem of kinetics exactly the way that we've tackled things before. We're going to write some rates down, some laws, write some rate laws down, apply a steady state approximation, and look at how the rate evolves as we make changes to the reaction. So let's think of a very, very basic reaction or a very basic process for an enzyme. So the basic idea, that's supposed to be a C, is that we're going to start in the body with an enzyme, which I'm going to call E, and a substrate, right? That's the molecule that the enzyme is targeting. We have an enzyme and a substrate. Right? And the idea is that we're going to bind that substrate to the enzyme. The enzyme is going to do something to it, make a new molecule, and spit that molecule out, right? Like a little factory. So the first thing that's going to happen is there's an association, a binding event. That's going to be an equilibrium. We call this binding, right? Where the substrate comes in and attaches itself to the enzyme, right? And that has a forward rate, which we'll call K1, and a reverse rate K-1. These may be different. They might not be the same. And what this will form is some complex of E and S together. Right, this is our complex. And the idea is that this is the actively reacting species, right? The idea is the enzyme is off. It's not doing anything. It's just waiting. And you bring a substrate in, it binds, and then you have this complex that is now activated. And now that's what performs the reaction. So what will happen is something will react. The system will catalyze, and it'll react. So this will spit out some product at some rate Kcat for K-catalysis, generating our new molecule P, and returning to us an enzyme. Right. So here I've put the enzyme in the stoichiometry, but notice it's a product and a reactant, so it's a spectator. Like there's no net stoichiometry of the enzyme. We're not using the enzyme. Only temporarily. The enzyme should return back to its original state after it's done, so we can take another S and convert it to P. Of course, it is doing chemistry. It is facilitating something, but in the end, there's no net stoichiometry. So it's acting as a catalyst. Okay. So let's write a few things. First, what we can write is an equilibrium constant for binding. Right. We'll define an equilibrium constant called K sub M. And that's going to be equal to the complex concentration divided by the concentration of the reactants. Okay. It's not hard to show this, but this is equal to the ratio of the forward and the reverse rates. Now, why is that? This is a really interesting point. In fact, this is a general result, is that the equilibrium constant for a reaction is always the rate of the forward reaction divided by the rate of the reverse reaction. This is a completely general property, something I can always write. And the derivation of this is very simple. Right. So let me just prove this to you in just a little sidebar. Right. We can write rates for the forward and reverse reaction. So the rate of formation of the complex with respect to time is equal to the rate of formation, which is K1, times the reactants concentrations. And the rate of formation of our products, our reactants, the backwards rate, which are equal to each other, is going to be equal to K minus 1 times the concentration of ES. Right? So we've got a forward reaction and a reverse reaction. We want these to be at equilibrium. When the system reaches equilibrium, that means the forward rate is equal to the reverse rate. So at equilibrium, we remember at equilibrium, microscopic reversibility applies. Microscopic reversibility says it's equally likely to go forward as backwards, which means that the rates are equal at that point. I have that, right? And now when I relate these two, I've got K1 times the reactant concentrations times K minus 1 times the product concentrations. All I have to do is divide things. I just take this equal to this, and I get that the products, right? Just write that. Just in case it's not obvious. Right. Have that. And now I just divide both sides by everything. And now I have that K1 over K minus 1 is ES over E times S, which is our definition of this equilibrium constant K sub M. Right. Easy enough. Right. So this is actually a really nice way sometimes to get some kinetic information, or vice versa. If you can measure these rates, you can measure equilibrium. If you can measure the equilibrium and you know something about the concentrations, you can determine something about the rates. There's lots of different ways to interconnect these two properties together. Okay, so that's a nice number to know. That's something we know we can measure. Right? Equilibrium is something that we can do in the lab. Right? And I want to define one more thing. I'm going to define the what's called the velocity of the reaction, which is just the product formation rate, dp dt, which is equal to k cat times the concentration of the complex. Okay, so we've got some numbers. We can certainly measure how we form our products, and then we can measure. This might be kind of hard to measure, the substrate, the complex. That's kind of a hard concentration measure because it might be only in existence for a short amount of time. So we need to do some manipulations, right? We need to think about things that we can measure, which would maybe be the enzyme or the substrate, for instance, or our products. We can measure equilibria, things like that, right? So let's try to arrange some things and see if we can learn something about the overall kinetics of this process. The first thing we're going to do is to say that let the current concentration of the enzyme be equal to the initial concentration of the enzyme. Right? So before you ever put a substrate in, you've got some enzyme in your body. And it's going to be that minus the enzymes that are complexed. Right? So some of them, you have some pile of enzymes in your bloodstream. Some of them have substrate bound to them, and so whatever's left is the difference. So what we can do at the very least, right? We can apply this approximation here and put it into our KM equation. Right? That's a measurement that we can measure through equilibrium. And what we find is that ES, the concentration, is equal to the initial concentration of the enzyme times the concentration of the substrate. Of course, if this is a drug, you know how much you put into your body roughly, plus this equilibrium constant, plus the concentration of the substrate. Okay, this is basically just steady state. Right? The idea is that the only situation that the enzyme can be in is either completely free or bound. Nothing else happens, and so roughly this amount stays constant. It's the idea that concentration of ES is flat pretty much through the whole reaction. Right, so we get this steady state concentration for our intermediate, right? That's what we want to do. That's why we apply steady state, is to cancel out all the effects of the intermediates that are short-lived, that we don't have to, that we can't really measure. And now, as you can see, I have a concentration for ES, right? So now I can write the rate of formation of my products as a function of this. So what I could say is that the rate of formation of my products, nu V, right, which is something I can measure in the lab, dPdt. Maybe I'm using UV vis, for instance. That's a really common way for these things to be measured. It's going to be equal to the rate of catalysis, right? How fast the enzyme reacts with the substrate, times, let me get it right. The initial concentration of the enzyme, times the substrate concentration. Sorry, this is Km, not Ks. I apologize. Call it Km here, over Km plus S. All right. Well, this gives me something that I can do. All right. So the thing is that I can measure. I've got some rates that I might not be able to measure necessarily. Kcat, I'm not really quite sure how to measure that. But I can certainly measure dPdt by measuring, say, the absorbance of the product as a function of time. And that's a really common way for these things to be done, right? So UV vis will do this. Right, and then you have some enzyme. You might not know what the concentration of your enzyme might be, but in some sense that's fixed to your body, right? You have some biological amount. We can quantify it, right, through an analytical chemistry, right? And the substrate is in some sense like your drug, right? This is just the loading concentration of your target, of your substrate. If it's a drug, if it's like an antidepressant or something like that, you give someone 10 milligrams and you say, hey, they've got X amount of blood. It's going to be roughly this many milligrams per milliliter of blood, right? So you can figure out that, get some approximation of the substrate that way as well. Of course, that's very hard to do in the body. The body has lots of different things. So there's obviously ways that you do this in you can measure these kinds of things in a closed, kind of a sealed environment, right? You can extract your enzyme from the body. Right? That's what you do in biochemistry lab half the time. You're extracting some enzyme from some process, you purify it, you put it in some buffer, right? You know exactly what this is because you did the separation, you did the analytical chemistry and the quantification. You know exactly how much enzyme you pulled out of your cell culture. And then your substrate, you're just putting in with a pipette. You know these numbers. So if your product is somewhat, you can measure it in some time resolved way, say through spectroscopy or chromatography or something like that. You can use that to measure this. You know, this number, this number, this number, and as we'll see, you can determine statistically what the value of Kcat is, right? So that's your unknown. So we have two big unknowns that we have to kind of resolve that experiment will tell us. Right? These are the experimental unknowns. Okay, so we need to figure out how do we take some information that, again, is not too hard for us to do, assuming that the process of separating this enzyme is reasonable. Some are harder than others. But there are certainly ways to do this reaction kind of in like a vacuum and be able to have to worry about all the different side products and the other things that your body does. All right, so how would we do that? Okay, so we can actually determine these things graphically. And I'll show you a couple different ways to do it over the next 2 days. Right. The first way to do it is to just go into the lab and make an XY plot, right? You do a series of these reactions, changing the substrate concentration. Right? We're going to fix some things. We're going to fix E naught, and of course, we'll fix the temperature and the pH, right? Just leave the pH constant as well. Those are generally the 3 important variables in biochemistry: the pH, the temperature, and the concentrations. Fix that. And what we're going to do is go look at our velocity as a function of substrate. Right? So we get something that is in units of moles per liter per second. And this is in moles per liter. Right? So this is the formation rate of our products. Right. Let's think a little bit about this reaction. Of course, if there's no substrate, there's no reaction. So we know where this curve should intersect. So if the substrate is, let me put it here, put it 0. Right, we know the rate is going to be 0. Right, and of course, as the right, that's half the step. We know it's there. The question, of course, is where does it end? Right, but we can figure that out. Right, because your body's going to have some fixed amount of enzyme. Right? Let's say for every mole, every milliliter of blood, there's 1,000. Okay, so that means that at one time, only 1,000 molecule enzymes can work at once. There's no other way to make it any faster. The fastest rate is when all the enzymes are being at 100% duty cycle. They're all being used constantly. So there's some maximum rate. Right? There has to be some maximum rate, which is we'll call Vmax. And it's, of course, a flat line. And this is basically where the enzyme has been completely saturated. Right? This is 100% use of E. Okay. And it's easy to think, well, Vmax then is just kcat times the initial concentration of the enzyme. Right? If there are that makes sense. If we have twice as many enzymes in a concentration, twice as much concentration, we can react twice as many molecules, which means that our Vmax will be twice as fast. All right, so we know that at large concentrations of S, what we're going to get is a situation where we're in excess of S. And if you think about the enzymes, this is the way I like to think about it, is the enzymes are cashiers at Walmart. And there's maybe, if it's a normal day, there's only 3 cashiers running. You can fit in 3 people. 3 people can come in, get cashed out just fine. But then you got 6, you got 3 people waiting, 1 in each one. You got 9 people, you got 2 people waiting in each one, right? You start to build a queue. And of course, it's totally fine to build a queue as long as the rate of the cashier is fast enough to push through those people. You don't get the line continuously expanding over time. Right? And of course, what's the only way to cut that down? The only way to cut that down is to double the number of cashiers. Then you can have 6 customers go at once, and your rate doubles. Okay, so we know that at maximum limit, this is going to asymptotically approach 100% like this. Right? And so it's going to have some smooth curve that just asymptotically approaches 100% like this. Okay, so we have a curve that looks like this. Right? We can define a 50% point, right, about halfway from Vmax. So Vmax over 2. Here. And we define the S at that point at Vmax over 2 We'll call this S1/2. This is the S that we defined Km to be at. So Km is the equilibrium constant. When the rate is 1/2 Vmax. All right, so the idea is that Km can be defined as some ES. Who knows what that is? Well, that's E 0 minus, what do I have? Sorry. E0 minus S over Km plus S over E plus S. And where S is at the 1/2 limit. It's kind of a complicated equation, but the idea is that you can go and just measure this, right? With your, you'll see that the rate will eventually topple at your conditions. It'll eventually slow off. And you say, well, okay, I find the S that gives me half the speed, and that's the S that gives me Km. Right. So the idea is that the smaller S12 the less S required to reach Vmax. Right. And this means that Km gets smaller. Right. So the idea is that effective enzymes, effectively binding enzymes, have a minimal value of Km. Right. We typically call for drugs, for pharmacology, Km is generally referred to as the binding efficacy. And it tells you roughly the concentration of drug required for clinical response. Right? So if you measure the Km for some drug that maybe is an inhibitor of an enzyme or something like that, we'll talk about inhibitors eventually. If you got some drug and your Km determines basically how big of a horse pill you need to give your patient. So if you have a very high Km, on the order of a micromolar or hundreds of nanomolar, for someone who's 100 kilograms, you got to feed them quite a bit of medicine, hundreds of milligrams. But some medicines are very, very effective and bind instantaneously. Basically, the moment they see the enzyme, they just hook right up. Delta G is very negative. And they have very, very small Kms on the order of nanomolar. So like a really, really good drug typically, like world-class drugs, tend to have Km of around 10 nanomolar. Right? And that kind of comes out to, give or take about 1 milligram per kilogram needed. Give or take. Factor 10 or something. Okay. So, for instance, Tylenol, for instance, is a medicine that it doesn't have a particularly strong Km. Which is why you take a gram of it pretty much anytime you want to take it. But, if you're taking, like Prozac or one of those drugs, they bind very, very effectively to their receptors. And you only need to take, 5 or 10 milligrams of it, maybe 20. Right. So those medicines are on the microgram per kilogram for clinical response. They tend to be on the order of 10 nanomolar. So if you go look at drugs, I don't know how big of a nerd you are or not, but if you ever go look at drugs on Wikipedia, you'll see these pharmacokinetics numbers, things like CHEM, other types of numbers like that tell you something about the efficacy and how strongly they bind and how much you really got to feed into the system in order to drive the equilibrium towards catalysis. Because if it doesn't want to bind very much, you're not going to get a lot of catalysis because you don't create a substrate. You don't create the complexes. You got to create the complex first. But there's a double-edged sword. Imagine you have a really, really strong KM. What does that mean? That means that forming the complex is really effective. And see that substrate comes in and binds to the enzyme immediately the moment it sees that it connects. But if KM is so strong and that binding is so tight, what happens when KCat is really slow? When the catalysis itself is slow? Well, then you've got a problem. Because now what happens is your enzymes get poisoned. So your enzymes now are getting stuck to the substrates, and they're not getting processed. So all of the idea is that if you start with all enzymes free, and they bind very effectively, but they don't react very fast. You have, say, 100 enzymes, they all get bound and make complexes immediately. It's very, very favorable. And then the body's got to sit there and wait for 10 hours for them to kick those molecules off because the reaction itself is very, very slow. That's not a very effective enzyme either. Because then you'll get there. I mean, one thing is that we'll talk about inhibitors, for instance, some enzymes bind to things so effectively they shut off, can't remove it. The enzyme becomes dead effectively. You just turn it off. And sometimes it's just they get caught up and they can't catch up. And what happens is you get more and more of the substrate built up in your bloodstream, and eventually, you get toxin. You get in fact, you get poisoned by that. A really, really good example, of course, of that process happening is alcohol poisoning. One of the key contributors to alcohol poisoning is that in some sense, your liver enzymes can't keep up with the concentration gradient you have of alcohol. Because what the body does to ethanol is to break it down into acetaldehyde through some sort of impressive process, the dehydrogenase, as it's called, liver dehydrogenase, which converts ethanol to acetaldehyde. If you've got so much alcohol in your liver that you've saturated all of your liver enzymes, then your alcohol is just sitting there and it's just infecting your liver and infecting your bloodstream and affecting the salt balance and the equilibrium of your cells, and it's just slowly killing you, right? And eventually it makes you sick and potentially die. It's because your enzymes can't keep up with the stream of alcohol, because then the alcohol seeps into little corners of your body where the liver can't deal with it anymore, and then you slowly get poisoned by it. Something that also happens with liver dehydrogenase, particular people that drink a lot of alcohol, their body expresses large amounts of liver dehydrogenase, right? Because you evolve. You say, I expect that my owner is going to feed me full of Tito's every day. I'm going to be ready for it. Right? That's tolerance. Part of the tolerance is your ability to express enzymes. And so you express those enzymes, so you have an overabundance of liver dehydrogenase. And the problem is that liver dehydrogenase is so good at breaking stuff down, it starts to break down other stuff. And in particular, Tylenol is a particular problem when you have a high expression rate of liver dehydrogenase in your body and you start to take Tylenol, it kicks in the dehydrogenase in full gear, that production, and you get a increased concentration of dehydrogenase in your bloodstream, and your liver enzymes get all fucked up, and your liver slowly eats itself, and you get cancer. So Tylenol in particular, and you also get other sicknesses as well from Tylenol in liver because of your body's overexpression and its expectation that when your liver is under siege from some chemical, that it's alcohol and you need to break it down. Tylenol is something that affects that, right? So it's a very, very complex situation. You want your enzyme to be effective, you want it to bind strongly, but you want it to be fast, but you don't want it to be too slow. Right? So you've got to balance these two things of binding and speed. And we'll look at that over the next week, right? We'll look at some examples of how these two things modulate. Okay, we've got 15 minutes. Good. So let's look at an example. Let's actually just finish this up really quickly, right? So, Another thing that's useful to look at here, we go back to the equation we had for the rate here. And we do this at small levels of concentration of S, right? So if we look at the velocity of the reaction when S is basically zero, right? We just put in one molecule of S and we look at how fast it gets processed. Well, we've got some prefect on that small up here. This S is basically goes to zero. The denominator of this looks like Km. So what we can look at is the slope of this curve at small s. So like right here, graduate there. And what I do is I take a derivative of the curve at that point. Take a derivative. Look at that point right there. So it's small s. And what you end up getting here is that you get a rate here, right? We have some speed or acceleration, if you will, of the rate as you change S. That's what that tells me, the change in the rate as a function of the change in concentration. So this is also a rate. And what you find is that the rate that you observe here is the maximum rate times the concentration of substrate you put in, which is small, divided by Km. This rate here, we'll call it V prime. There's the slope of this curve. And that's equal to the maximum rate divided by Km. So if I can measure this asymptote here, I get V max. And of course, I can measure the concentration of S. That's easy. And I can measure this rate from my calculations, right, from my observations. So that gives me the value of Km. Right? So just by doing this graphical thing, right, if I could just measure how fast my products can form, and I know roughly where it saturates and the rough slope at low concentration, I can determine all my properties. I can determine the equilibrium constant. I can also determine the maximum rate, which tells me something about the catalytic rate of the reaction. Okay, so I didn't give this a name. So this is a theory. It's named after two white guys that are well known in the biochemistry community. This was published in the early 1910s, early 1920s, just the beginning of biochemistry and something. This is what's called the Michaelis-Menten model. And again, there's nothing really special about the Michaelis-Menten model. All we've done is just write down what we roughly think the reaction is and apply steady state to it. It's nothing special, but this was so novel in biochemistry they gave it a name. In chemistry, we just call this steady state. It's called Michaelis-Menten. Michaelis-Menten is the original way to measure enzyme and enzyme kinetics. And it works fairly well. There are places where it fails, but by and large, the vast majority of kinetic analysis in biochemistry comes from this approach. Okay. So let's look, how much time do I got left? Yeah, good. Let's look at an example. All right, so let's look at a special kind of enzyme, or rather a substrate that can affect our enzyme. Right, so what I want to look at is inhibition today. We'll start looking at the idea of inhibition. I don't want to have a 1 there. Right, we'll start it today and we'll finish it up next class. Right. We're going to talk about two different kinds of inhibition. So an inhibitor is a substrate that either slows or stops an enzyme from performing its duty. Okay. Oh, you think of it as something that slows something down. Thus in the word inhibitor. It's a really, really simple idea. We're going to look at two different types of inhibitors. I'll talk about them. We'll start them today, and then we'll do the analysis next class. The first kind is called a competitive inhibitor. And this is one that competes directly with the substrate for binding, right? So it competes directly with S as an alternative substrate, right? So they go in the same place, right? So the idea is that we have an enzyme. It's an equilibrium. We can add a substrate, and it has some equilibrium constant Km. We add substrate. Let me write it like this instead, plus S, right? And we make ES, our complex, and this goes to react Kcat E plus P. Okay, so we have this option. The enzyme can take a substrate and do its reaction, but it can also react with an inhibitor at some other rate, which we'll call Ki, some equilibrium constant Ki. That's our inhibition rate, to form some other complex EI, which is our inhibited complex. And then this reaction doesn't do anything. No reaction. All right, classic example of an inhibitor. Right? The idea is that the inhibitor crowds out the substrate and they compete for binding, right? So an effective inhibitor is a molecule that, one, has no co-cat, but also has a stronger binding affinity than the substrate. Not surprisingly, that can be a really hard thing to find sometimes, right? You've got to find something that not only binds more effectively than the substrate that the protein or the enzyme was designed to attack, but also you need to turn the reaction off as well. Right, so let's just do, and before I'm not going to do the kinetic analysis today. We'll come back to the analysis. Let's look at the other example. So another type of inhibitor called a non-competitive inhibitor or a mixed inhibitor. All right, we'll look at those two examples. They're related to each other. All right, so we start with our enzyme. Our enzyme can bind with S at rate K, equilibrium constant Km, to form ES. Of course, this can move on and react at Kcat to form E plus P. We can also bring in our inhibitor like before. At some equilibrium constant Ki to form EI. But the idea is that the inhibitor binds somewhere else besides the pocket that the substrate goes to. So the idea is that the enzyme has multiple places for things to go, which is actually quite common. Some things have multiple places for things to bind effectively. And that this is also at equilibrium with S. Right? This is, we'll say roughly it binds at the same equilibrium, ESI. Right? And that this can also react at some other rate, hopefully slower, form E plus I plus P. Or, well, we can say EI plus P. Right. So the idea of this is basically like this. If our enzyme has two little slices that, here's our enzyme and our substrate fits right into this spot right here. And so this is our complex ES. And this kicks out some molecule. This is E. And then we have some new molecule P. So some other shape. But the idea is that we can come in here, and of course this reacts at some K-cat, and this has some binding constant Km, right? But the idea is that another object can come in to the other side. We have some inhibitor that we can design. It goes into there. We have a new intermediate now. EI. And now that substrate can come into here, right? But maybe that shape is right. Maybe I has brought in and it's changed the shape a little bit of the substrate pocket. Right? Maybe I can give it just a little bit of fudge, right, like that. And maybe the fit isn't quite as good anymore. Maybe it's kind of curved it a little bit. And now the substrate kind of sits on the side like this, right? And there's this little fudge on the edge, like it's not a great fit. And there's, of course, a substrate here, or the inhibitor here. This is ESI, right? And this is going to react at some other rate, K prime, cat. So now give me my enzyme, my inhibited enzyme, with my funky little shape. So slightly different, right? Here there's no reaction. The inhibitor turns it off in the competitive one. But in our mixed case, the inhibitor is modified, right? So the enzyme is modified instead. Enzyme behavior modified. Right? It might be turned off, might not be. There are some really great examples of situations in pharmacology where you want to slow something down, but you don't want to turn it off. A really, really great example of that is a medicine that probably almost all of us take. I don't want to say that. That's not fair. Let's say a very large number of people take, which is Prozac, SSRIs in general, selective serotonin reuptake inhibitors. Yeah, that's right. And I won't exactly go into the reuptake process, but the idea is that your neurons and your transmit neurochemicals across the axons with some concentration gradient. We've got some serotonin on one side of a neuron versus the other side, got some concentration gradient. When that neuron fires, the neurotransmitters are transmitted across the synapse. And so you can kind of think is that you have in your neuron, you have kind of a source of those neurotransmitters and a sink for those neurotransmitters. And ideally it should go in as a loop, right? So you want to recycle those neurotransmitters on the receiving end and bring them back, right? You want to reestablish a concentration gradient, basically. So again, everything is a cycle. It's an equilibrium cycle in the body. You want to establish this concentration gradient. Well, that's a complicated process because you have serotonin on one end of the synapse. It has to get fed in through the synapse, cross onto the other neurotransmitter. There's some repository for those neurotransmitters on the receiving end. And then some object's got to take that neurotransmitter on the receiving end and shuttle it back to the beginning. Right? There's got to be some shuttling process. What happens with reuptake, right? The reuptake process is that recycling process of taking neurotransmitters, expended neurotransmitters, and bringing them back and refreshing them. It's a recycling process. And what people have with clinical depression who take SSRIs is that their reuptake is too effective. So what they do is it pulls too much. They're too effective at pulling the serotonin out of the receptors, if you will. And so it drives the concentration gradient through Le Chatelier's principle to generate more serotonin on the other side to reestablish the concentration gradient. So as you pull more and more away, it creates more and more. So there's this. So what you do is you have this positive feedback loop where the concentration of your serotonin increases over time. and goes above a certain level and doesn't regulate back down to some steady state. Right? The idea is not about having low serotonin or high serotonin, it's about having steady state serotonin, as well as having a good level as well. That's important. But reuptake in particular is about maintaining a steady state concentration. And what happens with reuptake is that it's generating it too much and driving the equilibrium too far in one direction. So what a reuptake inhibitor does is it attaches to those neurotransmitters, the reuptake process, some enzyme or some protein that does that. And it slows it down. It says, hey, don't process them so quickly. Please continue to process my serotonin. I need it, but I don't need it as much and as fast as I do. And so Prozac in particular is a selective and a mixed inhibitor that slows down the reuptake cycle so that your body will then process serotonin and maintain a steady state concentration of your neurotransmitters at all times, which is why it takes so long for it to work. Is that it takes a long time for equilibrium to be reestablished. You have to do it over every neuron, over every part of the body, along the wherever in the brain, I guess. It takes a long time to reestablish that equilibrium because it's constantly moving like this, and you're basically taking something that's oscillating very, very fast, and you have to kind of average it out and smooth it out over a long period of time. That's why it takes 6 weeks. That's also why it kills you when you stop taking it, and other things like that, right? It's a very complex process, and that's an important type of inhibitor. All right, so what we'll do is we'll think about the differences of these two things. How can I determine whether something's competitive or non-competitive? So we'll look at that. We don't even have to look at the structure. We can use kinetics to determine it. So we'll look at that, and then we'll look at things that speed things up as well. All right, we'll see that Wednesday. Have a good one, guys.
Straight to the. That's the. Somebody gas.
Yeah. No, it looks so. It was my first few questions when I asked her. No, really buckling to it's in my slots. It's in day shift. I was on today. And actually, he submitted.